and let's look at diffusion in relation to Kroger Vink. So previously, let's look at our old friend. Let's remind ourselves about some of our defect reactions, and let's look at our friend KCl. So let's assume that there are going to be intrinsic and extrinsic reactions. And we want to describe the diffusion because, again, KCl is what type of crystal? An ionic crystal. So what type of diffusive mechanism will dominate? Well, it's going to be the diffusion of vacancies. So let's go ahead and write a reaction to kind of show how the diffusion will change as a function of basically the concentration of these vacancies. So let's go ahead and write it out. So there's going to be intrinsic and extrinsic reaction. Right now, let's focus on the intrinsic. What are the types of intrinsic reactions that can occur for KCl? Well, we could have Schottky or Frankel defects. For the sake of argument, and again, you can be given a problem where you're given the enthalpy of formations, like in problem set 3. Let's assume that the dominant reaction is the Schottky reaction. So we know that the delta HF of Schottky is less than the delta HF of Frankel. So our Schottky reaction for KCl is just going to be null, and then we go equals or dash vacancy of K plus vacancy of Cl as this. So this is the reaction, the intrinsic reaction to form these vacancies. So, but now we want to kind of go a little bit of a step further. So there's going to be some type of energy required in order to kind of create this reaction, and some concentration. This is basically a chemical reaction. So we could write out what is going to be the equilibrium rate constant for this reaction. So it is going to be, again, concentration of products over concentration of reactants. Reactants, there are none, so concentration of VK, concentration of VCl, and that's going to equal exponential minus delta G, or actually delta G formation of Schottky defects over KT. That is kind of our rate expression for this reaction. So KEQ, we could also call it K Schottky, is just going to be, again, these brackets denote concentration. So our equilibrium concentration of reactions is going to kind of go as a function of this Arrhenius relationship again. And you can call it GS or WGS. So the kind of steps in this, whenever you're dealing with Kroger Vink notation, is first, for intrinsic. So let's do intrinsic. We need to do a couple things. So first, write the reaction. So null goes to, basically vacancy K plus vacancy Cl. 2 KEQ equals K Schottky equals our exponential minus GF sub S divided by KT. We also, what is our condition for charge or electrical or charge neutrality? Well, we know that the concentration of this vacancies must be equal to here. Must be equal to here. We're going to do another example where it's going to be a little bit different, but we know all this is saying is that to be charge neutral, I can't have this being more than this. Otherwise, I'm going to have I'm going to have a net negative charge. So to be charge neutral, I need these concentrations to be equal. So again, you could kind of then yield how is the basically the concentration of vacancy is going to be as a function of this formation energy as well. So with this, we can, once we have these expressions, we can write how can we describe the diffusion of K? Well, the diffusion of our potassium ions is going to be our typical expression here, R squared F divided by 2D. Well, we'll assume that F is equal to 1, D is equal to 3. R squared is just going to be in our FCC, again, on our kind of lattice, we'll just kind of, again, this is going to be some distance. Let's just call it A squared. But the important thing is here. We saw last time when we were dealing with the diffusion of FCC, we moved based on our number of nearest neighbors, right? So the number of options or number of places we can kind of hop to. Well, if we're looking at the diffusion of K atoms, if we are, excuse me, this should not be Na, this should be K right here. So if we're looking at the diffusion of K, where are we kind of moving to? Well, we need to be able, our hops are going to depend on, are basically going to be proportional to this the concentration of these defects right here times your tau prime. That's it. So we have an expression. So we know that this kind of tau prime, for example, is going to be this nu times exponential minus g of migration divided by kt. So we can kind of plug in, and for the rest of this kind of expression, so we know that this is also equal to minus g formation of Schottky over 2kt. Because again, all I'm doing is, right here, right? So once I have my electroneutrality equation, I could kind of plug back in to this expression right here and get, excuse me, this should be this value right here. So once I know that these are equal, I can kind of plug back into here and then get this expression. Because if I know that this must be equal to this, then I know that Vk dot, I could plug in here, Vk dot equals exponential minus g formation Schottky over k. There we go. So then that becomes, again, now it's just math at this point. So Vk prime equals this exponential over 2. So you plug that into the expression, you add this, and you could get this expression here. Or, again, a little bit more simply, a squared nu exponential of minus g of migration minus g of, you could actually break it into parts, over kt minus plus g formation of Schottky over 2kt. There it is. So we could describe now the diffusivity, and again, this is only in the intrinsic regime. What happens though if, again, you can kind of see where it kind of leads into. What if we have an extrinsic reaction? Well, so let's go ahead and look back at this. So if I have the following defect reaction, if I'm incorporating CaCl2 into KCl, I could write this substitutional reaction. So I've got my reaction. So again, the first step is to write the reaction. So the next step would be, again, what is the rate constant, right? But is there some type of equilibrium or in this extrinsic reaction, is there some relationship with temperature? No, there is no relationship with temperature here because we're inserting, in order to create this vacancy in the cation, we are putting in the energy ourselves. So we're extrinsically putting in that material. We're creating this cation substitutional, and we are thus also creating this. So there is no temp relationship because this is an extrinsic reaction. So no relationship with temperature, at least up to this point, to create the reaction. So it's just the energy that we're putting in. So in order to create our charge neutrality here, it's just going to be that our Ca, this must be equal to this. That's our expression for here. So again, here there's no kind of concentration here. So we can use this and plug it back into and see how our temperature, how it goes as a function of temperature. But we know that this is not going to be a function of temperature. So for the extrinsic reaction, when we jump down to how is our diffusivity going to change, our diffusivity of K, it is again going to be this expression here, where it's concentration of Vk times your tau times your r squared times your f over 2d. What do we know about our electroneutrality expression? Well, this just is going to be the energy here. Does this have any kind of value or any, has anything to do with our concentration or our temperature dependence? No. So instead, your diffusivity is just going to be this concentration, okay, times your nu a squared exponential minus gm t. That's it. That's your expression for the extrinsic reaction. So now the question is, what, we have an intrinsic and an extrinsic reaction. Where does each dominate? Well, in the intrinsic case, actually, so let's see, in the extrinsic case, actually we can plot, ignore this here. There's a little bit of a typo right there. So let's go ahead and see where each of the cases dominate. So intrinsic, we're looking at where the reactions will be dominant. So let's go back and look at the intrinsic case. So let's go all the way back over here. So in the intrinsic case, we saw that the concentration of vacancies was proportional to this Arrhenius relationship right here. Actually, right here. So in the intrinsic case, that is going to dominate at very, very, very high temperatures. So intrinsic dominates at very, very high temperatures, not low temperatures, high temp, and very small concentrations of Ca. So we can plot essentially the concentration of vacancies, of these cation vacancies, and the concentration of as a function of temperature and as the diffusion as well. So we know that here the concentration is just simply this for extrinsic. So let's go back and let's go ahead and write out the full expressions. So it's kind of nice to look back and have this all kind of on the board on the same page. So for our extrinsic case, we saw that our K equilibrium or our concentration of vacancies is just going to be related to this. That's it, or the log of those concentrations. They're directly proportional in our extrinsic case. For our intrinsic case, we saw that the concentration of our cation vacancies was proportional to this GF of S of over 2kT. So you could rewrite this instead of H of F, it is just going to be basically the slope here is going to be this minus EF of Shockey over 2K because we're plotting as 1 over T. And you can see in this plot, in the intrinsic side, at low values of 1 over T, where are we at? This is at high temp. Extrinsically, we're at very, very low temperatures. Why does extrinsic dominate at low temperatures? Well, because we don't need, again, we're supplying the energy. We don't need temperature to create our reactions. We're putting in these CaCl2 ions. And when we put in this, it directly creates this vacancy as well. So we're putting in the energy. So extrinsic is going to dominate at low temperatures, and it will be modulated solely by this kind of concentration. And when we look at the diffusivity here, you can see we still keep this kind of enthalpy of formation, but we have to add this energy of migration, minus G migration over KT, over K. So that is kind of the key idea between writing this expression of the log of this versus 1 over T versus this as well. So we could write and kind of calibrate these relationships. And so that's kind of the key idea that we're looking at here. So when you go back and when you rewrite these expressions, you can kind of see how these concentrations develop. And you can see here, they're just directly, it's essentially directly proportional. So you don't have to kind of worry about those. All right, so with that, we're going to finish up this lecture by looking at the fact that diffusivity will change, or actually it's dependent on this local environment. So we're going to do a couple more examples on this intrinsic, extrinsic, and so be able to be on the lookout for those videos. Thanks. I'll see you in the next video.